Jen, you mentioned that I worked in industry, and I found that when I worked for teams, there was too much emphasis on winning games and not enough emphasis on solving puzzles. So that's why I'm really glad to be back in academia now. So I've got 3 fun projects to share with you all, really just to advertise. And here's the structure. We'll just go through them one by one, and here's a sampling of the type of statistical methods that we'll be using in each of these. The first one, which I'm calling pickoff game theory, was a project by my student Jacob Hahn, who was an undergraduate at Rice and is now, he's graduated, he's going on to the Chicago Cubs, along with Malesh Pai, who's an economics professor, and Andrew Schaefer, who's an OR professor. And the idea here is that in baseball, when a runner gets on base, they can try to steal the next base at any time. And typically they won't stand on the base that they're on, but they'll take a lead off of that base in order to make it easier to steal the next base. And the primary deterrent that pitchers have at their disposal is called a pickoff. So they can, instead of pitching the ball, they can turn around, throw the ball back to the base, and try to tag the runner out. Now, going into 2023, MLB made several rule changes to make the game faster paced, more exciting. And one of the rule changes that they made was that they limited the number of pickoffs to 3, so that pitchers just couldn't keep throwing the ball over to first base again, and again, delaying the game. So this introduced an interesting cat and mouse game between the pitcher and the runner, where with each successive pickoff attempt, the pitcher is disincentivized from throwing to first base because they get closer to that third pickoff. But that means that the runner is incentivized to extend their lead and try to bait the pitcher into throwing over to first. Because after 3 failed pickoff attempts, the runner gets that base for free. So the puzzle here is, if you are the runner, how should you extend your lead after each pickoff attempt? And we got some cool data from Major League Baseball we wrote in, and we got pitch-by-pitch lead distance data from player tracking. So for every pitch, we know for every runner how far off of their base were they leading, measured in feet. So our approach here is twofold. First, we want to estimate the effect of lead distance, and then we want to solve for the optimal lead distance. So when we're estimating the effect of lead distance, we're just going to use linear mixed effect modeling. We've got 3 models. We've got one for the probability of pickoff given lead distance, probability of an attempt. Then we've got the probability of a successful pickoff given that one was attempted. And then we've got a probability of a successful stolen base given that one was attempted. So we've got fixed effects for lead distance, of course, and then disengagements, which is our formal way of saying this is the number of previous pickoff attempts that the pitcher has made in this plate appearance. We've got the number of outs, we've got the ball strike count, and then we've got catcher arm strength and runner sprint speed, both measured in miles per hour. And these are measured on the player season level. So we don't have it on the pitch by pitch level, but these are player characteristics. So we estimate those models, we get probabilities of each of these events. That gives us transition probabilities for step 2, in which we model the inning as a Markov decision process. I wasn't really familiar with MDPs before I returned to academia, but they're such beautiful models. I feel like anytime someone uses an MDP to solve a problem, an angel gets its wings. So Nathan, thanks for all of the work that you do on that front. Okay, so we model the inning. The state space is the number of past disengagements, which bases are occupied, how many outs, and what the ball strike count is. And our action space is the lead distance chosen by the runner, anywhere from 0 feet to 20 feet. And our reward function is, when we transition between states, the number of runs that are scored on those transitions. So to show you what the results look like for step 1, here we've got on the left pickoff attempt probability and pickoff success probability as a function of lead distance. Unsurprisingly, both of these things are increasing as lead distance increases. But the reason that the runner takes a leadoff is to steal a base. So the most interesting one here is the probability of a successful stolen base, given that one's attempted, as a function of lead distance. So slowing down here, the solid gray line is the median runner in 2022. The solid blue line is the median runner in 2023, and the dashed blue line, that's the 10th percentile runner in 2023. So what we see is going from 22 to 23, even the 10th percentile runner had a greater chance of success stealing bases than the median runner in 2022. In addition to the pickoff rule, another rule that they changed is they made the bases just a couple inches bigger, which, because baseball is a game of inches, it turns out that makes a significant difference in their stolen base success probability, because the runner has less distance to cover when going from one base to another. An interesting thing about these linear mixed effects models is that because we have fixed effects fixed effect for sprint speed and also a random effect for runner. On the left here, what I'm showing you is an estimate of runner skill that's based on both the runner's sprint speed and also the random effect for the runner. Essentially, every runner skill is regressed toward an expectation based on their sprint speed. So this is a novel application for player evaluation in baseball. And then we have a similar thing for catchers and their arm strength, where we're evaluating catchers not just on their arm strength and not just on their outcomes, but by combining the information from the two. It's a neat little thing that fell out of this model. So we take these estimated probability models to get transitions between states, and then we use our Markov decision process to solve for an optimal lead policy for any given state. And this is a summary of what the results look like. I'll bring your attention to this third column right here. What we observed is that after the first pickoff attempt, we think that the runner should increase their lead by about 1.5 feet. And after the second pickoff attempt, we think that they should increase their lead by about 2.5 feet. And when you compare that with the actual behavior of runners, we see that they're a lot less aggressive. They're a lot more conservative when they're extending their leads as the disengagements are increasing. So some additional results that I haven't shown you here are, first, everything I've shown you here has been assuming just an average base runner. But we can vary the base runner skill, we can vary the pitcher and the catcher skill. And I've also assumed here that the pitcher is sort of a stochastic process. And so an interesting question is, well, what if the pitcher has agency and can deterministically decide whether to attempt a pickoff? And that becomes a game theory problem that we worked on. So the actual run value effect of choosing the optimal lead distance is pretty small, but we did some back of the envelope calculations to say that if all of your runners implement this policy over the course of a season, we can expect a team to score 20 more runs over the course of a season, which in free agency, teams pay about $1 million per run, so that's a $20 million solution if you're able to implement that. Now, I don't care too much for money, and that's why I'm an academic now. Project number 2, predictive pitch score. This is with Vicente Iglesias, who coincidentally was a Rice undergraduate and now does quantitative trading at SIG in Philadelphia. The background here is that for the past couple of decades, every pitch in Major League Baseball has been tracked, and the data are publicly available. Now, when I say that the pitch is tracked, the tracking is, the trajectory of the pitch is approximated as a 3-dimensional quadratic function of time, meaning that it can be expressed using 9 parameters. And at this point, it's become standard practice to evaluate pitchers based on these trajectories rather than based on the actual outcomes. In fact, Tim, I think it was you and your daughter who wrote the paper on this. But there is one issue with using these pitch trajectories to evaluate pitchers, which is, the typical approach is to treat this as some kind of supervised regression problem. You've got your predictors X, you've got the outcome of the pitch Y, and you make a prediction. The problem is that the most important features for predicting the outcome of a pitch are the least reliable features. So I'm showing you on the left variable importance from a gradient boosting model for predicting the outcome. The most important features for predicting the outcome of the pitch are the location of the pitch as it crosses the plate. And these two variables are also the least reliable. If you measure them in one sample and then in another sample for the same pitcher, there are other variables that are way more predictive. For example, the release point from the pitcher, the release speed, and the movement of the pitch are way more reliable predictors of what the pitcher is going to do in the future than the location of any individual pitch. So to drive this point home some more, typically in supervised learning, you observe data x1, y1 through xn, yn, and your goal is to learn a function f so that when you get a new query point x star, you can predict a y hat corresponding to that covariate value x star. Our problem is a little bit different. We still observe x1, y1 through xn, yn, but they're thrown by different pitchers, call them a, b, c, and then when we want to make a prediction, we don't have a query point x star, but rather we have a pitcher label a, and we want to predict what the outcome will be for pitcher a. So our approach here is going to be to use the x's to learn a PDF, to learn a distribution function for each pitcher. And then we take that supervised regression function f hat and we'll integrate it with respect to that distribution function that we learned. So in more detail, step one here is to estimate trajectory distributions, and critically, these are conditional on covariates. You got this distribution over the 9 parameters of a pitch trajectory. So it's a 9-dimensional distribution, and it depends on the count. Depending on the ball strikes, depending on the batter's side, the pitcher might aim to throw the pitch in a different location, or their trajectory might change in different ways. So we model this as a Bayesian hierarchical model. The likelihood is a 9-dimensional multivariate normal. The mean depends on the pitcher and the context and an interaction between pitcher and context. And when I say context here, I mean the number of balls, the number of strikes, and the batter handedness, like left or right. The variance scaling depends on the pitcher and the context, and the correlation structure depends on the pitcher. And again, this is a hierarchical model, and so we learn the distribution in between pitchers, as well as the distribution within each pitcher. There's information sharing between the pitchers. It's a pretty beefy model, so we just get the map estimator instead of trying to sample from the posterior for computational reasons. And then step two is once we have this distribution, we do the standard supervised learning thing, we do gradient boosting, we get our supervised function, and we integrate that function with respect to the distribution that we learn in step one. So to illustrate the results from learning that distribution in step one, here is a specific pitcher, a specific pitch type against right-handed batters. And what I'm showing you is the distribution that we learn for each count. The heat map shows the distribution that we've learned from the model, and the white dots are the actual data points that we observe for this pitcher. So here the number of balls in the count is varying as we move the columns left to right from 0 balls to 3 balls. The number of strikes is increasing from 0 to 2 as we go up in the rows from the bottom to the top. So what we see is that as the number of balls increases, the location distribution, I'm only showing you two dimensions of the 9-dimensional distribution that we learned, but the location distribution is moving more toward the center of the strike zone as the number of balls increases, whereas as the number of strikes increases, the location distribution is moving further away from the center of the strike zone. This all makes good baseball sense. But the reason that we do this is because we want to create better predictions of what the pitchers are going to do in the future. So the way that we test these predictions is we take that supervised regression model, let's call that the descriptive model, and we observe it in one sample, and we evaluate how well it predicts itself in a second held out sample. And then we take our predictive approach and we evaluate how well it predicts the same descriptive model in that held out sample. So are we doing a better job of predicting that descriptive supervised learning function than that function is doing by itself? So here I'm showing you the results depending on the training sample size. That's what's varying on the x-axis here. The light orange points are our approach, and the gray points are the descriptive supervised learning approach with some mean regression. So it's not entirely naive with how it's trying to predict future pitcher performance. And I'm showing you the correlation between the prediction in the training set and the value in the test set. So bigger is better, because we're looking at correlation. So what we see is that the predictive approach, it it provides the biggest benefit for pitchers with fewer than 300 pitches thrown in the training set. And to put that in context, many relievers will throw fewer than 300 pitches in a full season. And so this is valuable for teams that want to evaluate pitchers in small sample, or maybe be responsive really quickly when a pitcher has started to change their true talent. Maybe a pitcher has improved or gotten worse. By picking up on that signal more quickly in small data, teams can act more quickly in acquiring those players. Last project here was a really fun one with Ron Yurko over at Carnegie Mellon. And this was, we dubbed it Swinging Fast and Slow. And it was motivated when MLB released swing tracking data a year ago. So it's a really cool data drop where every single pitch, they report the speed of the bat and the length of the swing. Now, both of these things are measured at the point of contact, or in the case of a swing and miss, at the point nearest to contact, which will come up again in a couple of slides. But a natural question that you might ask from these data are, like, what are the consequences of the batter swinging harder, swinging faster, or swinging slower? You can imagine that a batter swinging out of his shoes every single time is less likely to make contact, whereas a batter with a more controlled swing might be more likely to make contact. So you could do a naive analysis. You could look at pitches that result in good contact or bad contact, and you can compare the swing speed from these two groups. And that's what I got here. The top density is the distribution of swing speeds relative to the batter's average on balls that result in good contact, and the bottom half is pitches that do not result in good contact. We see pretty much the same distribution between these two subsets. If anything, we see a counterintuitive result, which is that players on average are actually swinging a little bit harder relative to the player's own average when they're making good contact. So this is counterintuitive, and the puzzle here is, how should batters modulate their bat speed and swing length? This very naive analysis has not done a good job of answering that question. There are a couple of challenges here. One I mentioned earlier is about how the data are measured. You can imagine that two swings are exactly the same in terms of their mechanics. The speed through the swing, the length of the swing are exactly the same. But if in the first swing the batter is late, and in the second swing the batter is early, then we're going to measure bat speed and swing length at two different points along this swing. And so in that sense, these swing tracking metrics are actually outcomes themselves and not something that's entirely under the batter's control. And then, another challenge is confounding, and I think this explains the counterintuitive results that we saw on the previous slide, which is that if a batter is looking for a certain pitch, they start their swing and all of a sudden they recognize, oh, this isn't a fastball, this is a curveball. Well, now the batter needs to adjust their swing, maybe slow it down, maybe manipulate the barrel so it moves to the right part of the zone. That's going to result in the bat slowing down, and because they guessed wrong on the pitch, they're also more likely to miss the pitch. And so you've got these confounders. There must be some effect of swing length and bat speed, but it's confounded by this factor. So the approach that we took here is to estimate the batter intention. And the way that we did this was by filtering on well-contacted balls that are fastballs. So we're saying when the batter is successful, what does their bat speed and swing speed, what does their bat speed and swing length look like? This is a Bayesian hierarchical model again, now with a skew normal likelihood, which we found outperformed a normal likelihood in model diagnostic tests. Once we fit that model, what we see is that different batters modulate their swing differently according to the count. And so in step 2, we compared the batters who slow down their swings more versus less. Well, how does that change their performance in those counts when they slow down their swings? So this is sort of an instrumental variables regression from economics literature, where our instrument is the count. Putting the cart before the horse here, what we see is that there is a trade-off between contact and power, where you can slow down your swing for more contact, less power, and the question is the trade-off worth it? So here are the results of that intention model showing the interaction between batter and count. we see that there are differences between batters. Some batters slow down their swings more or shorten their swings more as the number of strikes increases as they're trying to make more contact. On the x-axis here, I've got how much does a batter slow down their swing as the number of strikes increases. On the y-axis, how much do they shorten their swings as the number of strikes increases. So once we have this, going to the instrumental variables regression, here are the estimated causal effects that we get for these changes. Here the left side is swing length, the right side is bat speed, the top row is contact, the bottom row is power. I want to bring your attention to the right side, where in the top right figure, we see a really strong relationship between how much the batter is slowing down their bat speed, going right to left in that figure, and how much more contact they're making in those counts. But we see the opposite relationship with power, where they're also getting less power when they slow down their bat speed. And then with swing length on the left, we don't see as clear of a relationship, and I think the reason we see any relationship at all is because swing length and bat speed are correlated on a pitch-by-pitch basis. So once we have this, we can now go back to the previous figure, and we can put a run value on the different batters in terms of how much they are slowing down or shortening their swing, because that's the gradient in the background here. This is on the run scale, and the difference between the best approaches and the worst approaches in terms of how batters are modulating their swings is pretty small. It's like 2 runs below average on the low end, 2 runs above average on the high end, which again, over the course of a season, works out to about $4 million. But I've already expressed that I'm an academic. Well, that's all I had. This is really just an advertisement for 3 of my projects. You can find all the details of these and other projects on my website. So thank you for your time and attention.